Picture this. You're out on a clear night, staring up at the Milky Way, when someone whispers, "Right now, a baby star out there is stockpiling enough stuff to build dozens, dozens of Jupiters." Pretty wild, right? But here's the kicker. That planet factory looks nothing like the neat pancake-shaped disks we see in textbooks. It's crooked, clumpy, and straight-up chaotic. I'm Blank, and in the next 10 minutes, we're diving into that cosmic construction site, asking one big question. How do planets form when the usual rules seem broken? Section 1. The first clue. First, let's rewind to how astronomers even noticed this thing. It wasn't a serendipitous, "oh look" moment through a telescope. Instead, radio astronomers spotted a weird blip, something that flat out refused to look like the tidy, symmetrical disks they're used to. They flagged it, Hubble's team picked up the baton, and the Wide-Field Camera 3 zoomed in. What was a fuzzy radio smudge sharpened into a lopsided ring of light. Imagine city traffic where every car piles into one lane while the opposite lane stays eerily empty. That's the vibe. One flank of the disk is puffed up and textured, the other looks oddly subdued. That imbalance is our first hint that something, or several somethings, has knocked the system off kilter. Section 2. Zooming out. The neighborhood. Now, step back with me. This star isn't growing up on a quiet suburban cul-de-sac. It lives in a crowded stellar nursery packed with newborn suns, shock waves, and leftover debris from earlier cosmic generations. Nearby radiation, rogue gas streams, maybe even hidden sibling stars, all of it tugs, squeezes, and sculpts the disk. Think of it as building a sandcastle while kids are kicking soccer balls all around you. Good luck getting perfect symmetry. Section 3. The race inside the disk. Here's where things get juicy. Inside the inner few dozen astronomical units, call it the star's front yard, gas and dust spiral inward, heat up, and glow. Farther out, colder clumps try to collapse under their own gravity, while turbulence and radiation keep shredding them. In some patches, gravity wins. In others, chaos wins. Hubble has basically caught a high-stakes race in real time. And that makes this disk, nicknamed Dracula's Chivito, a pristine test case for two rival planet-building playbooks. 1. Slow and steady. Solids drip together, form rocky cores, then those cores gulp gas. 2. All at once. Big hunks of the disk collapse almost instantly, skipping the rocky core step. Because the disk is both massive and wildly uneven, local gravity isn't shy. It can carve dense knots fast enough that our computer models can finally keep up. Section 4. The plumes and the rainfall effect. Look at those towering plumes Hubble catches on one side. Material has been hurled high above the disk's midplane, then rains back down in arcs. It's like a cosmic sprinkler, except it waters only certain spots. That directed rainfall piles mass into narrow rings or spiral arms, prime real estate for future gas giants. It also shuffles angular momentum, deciding how quickly gas drains inward and how long the disk can stick around. Section 5. Why timing matters. The star itself is ridiculously young, so we're peeking in before the usual cleanup crews. Stellar winds, radiation, magnetic fields smooth things out. That timing is gold for theorists. If a simulation can't recreate this level of asymmetry, vertical structure, or mass distribution, the code is missing something. Maybe realistic turbulence, radiative feedback, or clump migration. Future infrared and radio snapshots will show where big dust grains hide, where gas still dominates, and which zones are flirting with collapse right now. Section 6. Turning chaos into a map. Think of the disk less like a calm construction site and more like a city undergoing surprise urban renewal. The densest city blocks are where future gas giants will stake their claim. The quieter outskirts? Probably belts of icy debris. By mapping brightness at different wavelengths, astronomers can pinpoint where dust clusters, where gas heats up, and where empty lanes hint at unseen baby planets already carving paths. Follow-up with ALMA and the James Webb Space Telescope will give a 3D time-lapse, dust, pebbles, gas, each in motion. If researchers can link a narrow arc here or an abrupt brightness break there to a specific collapse stage, they'll build a Rosetta Stone for other, fuzzier disks. Section 7. Bigger Picture. What it means for planet hunters. Here's the takeaway. Future surveys may have to look for worlds in weird neighborhoods, tilted orbits, clustered giants, even failed clumps adrift between stars. Subtle twists of light in Dracula's Chivito could become a guidebook, helping mission planners decide which young stars are most likely to host the strangest planetary families. And as telescopes sharpen their gaze, this disk stops looking like a one-off oddball. Instead, it hints that even so-called normal planetary systems, including our own, may have started life with a serious case of growing pains. Personal reflections. Before we wrap, let me toss 3 quick reflections your way. Think of them as cosmic homework. 1. Pull up Hubble's images of the Orion Nebula or this disk. Spend 1 full minute just staring. Can you picture Earth's atoms being forged in that kind of mess? 2. Where in your life are you writing off chaos that might actually be raw material? Name one messy project, emotion, or idea and give it 15 minutes of focused attention this week. 3. Planets take millions of years to form. What's one long timeline goal you care about? Today, take a single, concrete step toward it. Respect the slow burn. Recap, tying it all together. So, here's what we covered today. First, Hubble zoomed in on a lopsided, Jupiter-rich disk radio astronomers flagged as weird. Second, that disk lives in a rowdy neighborhood, and the chaos around it is bending the rules of planet formation. Third, inside the disk we're watching 2 rival construction crews, slow and steady core builders and quick collapse heavyweights, race for dominance. Fourth, towering plumes are raining material into specific lanes, setting up future orbits and timelines for giant planets. And finally, this single system could rewrite our playbook for finding and understanding planetary families across the galaxy. If you remember nothing else, remember this. Planets aren't born in tidy nurseries. They emerge from turbulence, imbalance, and a whole lot of cosmic mess. And if the universe can turn that kind of chaos into something as beautiful as a solar system, just imagine what your own messes might become. I'm Jank. Thanks for listening, and until next time, keep looking up and keep embracing the chaos.